The arm on which we have the camera moves in the 3D space and can acquire pictures of a given plant from any point in this 3D volume. And then from this set of pictures we can obtain very detailed point clouds, 3D reconstruction of the plants. And from this we'll develop algorithms to segment this point cloud, identify organs automatically, and then measure any quantitative data that we want on the plants. So this is like the X-Carve CNC machine. It just allows movement in 3D. Here, instead of the CNC tool, we have this rotating arm, which is made of 3D printed parts, which will be available on GitHub. And then the sensor is just a RGB mirrorless camera that can be swapped for any kind of good quality camera. So most of my time is spent developing this algorithm to process the data that we acquire with the 3D scanner. So we developed this pipeline, which takes an acquisition of an Arabidopsis plant, and which reconstructs does a 3D reconstruction of the plant, and then produces a measure of the angles between the successive organs, as well as the internode distance. And this works on like some specific cases, but which could theoretically be already useful to the biologists once we validate them more. So the pipeline consists of several components. Some of them, like from the 3D volume, the segmentation and the measurement of angles, that is completely developed by us. There is a common library for the hardware and the control of the scanner. Then some components use open source software like Colmap. It's a very well-known photogrammetry software, which is completely free and open source. Potentially, the algorithm that we developed for this indoor phenotyping station could be transposed to outside phenotyping, since the components are mostly the same that we use on the rover. It could easily be put in the field.